Alright, so in this video I'm gonna be explaining another important paper with the title KerGNN, interpretable graph neural networks with graph kernels. This AAAI paper in 2022 from IBM. Graph kernels are historically the most widely used technique for graph classification tasks. However, these methods suffer from limited performance because of the handcrafted combinatorial features of graphs. So, graph neural networks have become the state-of-the-art method in downstream graph-related tasks due to their superior performance. So, to address the limitations of existing graph kernel and GNN methods, we propose a novel GNN framework termed KerGNN, which integrates graph kernels into the message passing process of GNNs. Inspired by convolution filters in convolutional neural networks, KerGNNs adopt trainable hidden graphs as graph filters, which are combined with subgraphs to update node embedding using graph kernels. So you see, this is the 1WL test. 1WL graph isomorphism test cannot distinguish one hexagon and two triangles because of the same neighborhood multisets. So here we want to combine graph neural networks with graph kernels. So we need some background. Like in previous papers, we had some base kernel. Now we can see the similarity of two graphs G and G prime based on the base kernel that is centered around nodes V and V prime. And so performing a random walk on the direct product graph is equivalent to performing simultaneous random walks on graphs G and G prime. But this product graph is not biologically inspired. The way they create the product graph, of course. And so here we define the vertex attributes of the direct product graph, and then the node attribute matrix S of the direct product graph is calculated by multiplying just x1 and x2 transpose, which are node attribute matrices of G1 and G2. So we flatten S into vector S. For ease of notation, we integrate the encoded pairwise similarity. So what is the proposed method? First, we need to define what is graph filter, what is feature mapping. The ICE graph filter at layer L is a graph H sub I with N sub I nodes. It has a trainable adjacency matrix and node attribute matrix. So each node is equipped with a subgraph and feature maps, which are transformed to phi sub 1 of that node in a way such that neighbors' local information, which are topological information and node representation, contained in G sub V will be aggregated to the central node V. We then rely on graph filters H sub I. So we have D sub 1 number of graph filters to obtain this phi sub 1. We calculate phi sub 1 by projecting subgraph features into i's dimension using kernel function value between graph filter and a subgraph. So we adopt a random walk kernel, which is introduced in equation 2. After calculating the kernel value of subgraph V, with respect to every graph filter. So it's very simple. The forward pass, you just calculate the subgraph and then calculate the kernel of the of a subgraph centered at node V, and each of the Isabelle number of filters. So Isabelle number of filters, Isabelle number of times you should calculate this kernel to create this valuable feature. Then you can guess what happens next. You just concatenate them, and then now you have a representation for graph. You can do it for graph classification. Then the rest of this paper is just about expressivity of subgraph-based aggregation, and also connections to convolutional neural networks, which was the motivation of this paper. And they did some experiments on these popular data sets like NCI1 dataset, protein, DD enzymes. And this is the mean accuracy and standard deviation of, for example, enzyme of this model. And you can easily see how beautiful it is to compare filters in convolutional neural networks and kernel GNNs. But is it really biologically inspired or not? That's a big question. So this was the motivation that is written in the appendix. Connection between kernel GNN also with message passing neural network. These are in the appendix. And so these are the graph filters that are discovered for MUTAG. Mutagen dataset is very important. Even if you want to do some interpretability, some explainability, it's very important.